Today we're going to be learning about how to model linear motion using parametric equations. And in order for us to create the equations we're going to use, we need to remember some things about vectors. So just going to start off with a warm-up about vectors and then move into a new way of thinking about slopes of lines. So starting off with warm-up number one, we're going to just find these three vectors given these points. So this one is basically the standard position from the origin up to the point, so it's pretty straightforward. We just use vector brackets. Same thing with this one, we're just going to use vector brackets. And for this one, we have to do head minus tail. So I'm going to take B's value and subtract A's x value, and then do the same thing, B's y value and subtract A's y value. And I can just rewrite that, so that's -7, -8. All right, question 2 is getting us to think about lines and their slopes in a new way. So we have, we're moving from point A to point B in 3 seconds. So what I'd like to do first is just figure out what is the change in just the x values. Okay, so I'm going to do the change in x, remember the triangle means change, and I'm going to, just like we did with the vectors, I'm going to do the head, or where we're moving towards, minus the tail. So I'm going to do -4 minus 2, which gives me -6. Do the same thing for the y values. So that's going to be 6 minus a -3, so that's going to be +9. And then we get the change in time. It's just going to be 3 seconds, because we went from no seconds to 3 seconds. Okay? So part A is asking us what is the rate of change of just the horizontal movement. All right, so rate, remember we can use that lovely equation that distance equals rate times time. So if I solve that for r, it's just going to be some distance over time. So if I want to know the horizontal movement and its rate, I can take its distance, which is -6, and divide by the time, 3. So I know that the change in the x value over time is going to equal -6 over 3, which is -2 units per second. Now for part B, what we want to do is come up with an equation that just models the x equation over time. Okay, so nothing to do with y, just what is x doing over time. So we already know that its rate of change is going to be -2 units per second. Okay, so I know that x starts at 2, okay, because that's the x value that we start at, and it's changing at a rate of -2 units per second. Okay, so I can write this as a -2 and then t. And let's just make sure that this works. So if t were to equal 0, and we plug it into this equation, I get 2 minus 2 times 0, so that's going to be x equals 2, which is what we wanted it to be, way over there. Now what if t equaled 3? Our x value should be -4, because we know that we travel from A to B in 3 seconds. So if I plug in 3, I'll have 2 minus 6, and that will give me an x equals -4. So this equation works. It starts us at A and it ends us at B in 3 seconds when we look at just the x values. And that's what we want. C is very similar to what A is all about, except this time it's vertical motion. So I'm going to do the change in the y value over the change in time, which is going to be 9 over 3 from up here. And so I know that the rate of change for the vertical motion is just going to be 3. So when I get down to part D, I'm going to do something very similar to what I did up here. I'm going to say, all right, the y equation, it needs to start at -3, okay? And it's going to change by 3 units per second. Probably should have labeled that up here. So I can write 3t. Okay, so I'm putting the rate of change multiplied by the variable of time. And let's just do our check again. So if I let t equal 0 and t equals 3, I just want to know what does y equal at both of these times. So if t equals 0, I get -3, which is what I wanted. And if t equals 3, this is 9, and 9 minus 3 is going to be 6. So this worked, okay? So together, these two equations will model this motion up here, the path from A to B taking exactly 3 seconds. And that's basically what we're going to be doing today. So before we continue with the line stuff, let's just finish up warm up 3a and b. So we're just trying to eliminate the parameter and put it back into rectangular form. So right now it's in parametric form because we have x defined by t and y defined by t. So there's three variables. Rectangular is when there's just x and y. So I'm just going to solve one of them and substitute it into the other. So I think this one would be easier. I can cross multiply this t up to the other side, and then I'll actually just divide by x. So I get that t can equal 2 over x, and then just substitute that in right here. So I'll get y equals 2 over x minus 3. We don't have to do anything else with that. X is in the denominator, so I know that this is a rational function. Ta-da! Done. For 3b, I'm hoping that you're starting to recognize that maybe when there's a sine and a cosine in here, that this might end up being some sort of circular type shape or a conic section maybe. And whenever I see both sine and cosine, my ultimate goal is going to be to substitute these into this equation here. So I need to isolate the sines and the cosines and square both sides. So let's add the 2, divide by 3, and that's what cosine will equal. And then I'm just going to square everything. So square that, square that, square that. Same thing over here. Subtract the 1, divide by, this is tricky, right? I'm going to divide by a negative 5 this time around. And that equals sine t. Let's square it. It's important that we're squaring the negative sign as well. So down here I get the sine value and the cosine value, and I'm just going to write them the other way around because we typically put x first. So I'll get x plus 2 squared over 9 plus y minus 1 squared over positive 25 because the negative is going to go away. And here we go. It's plus sign with both of them squared, so this is going to be an ellipse with a center at negative 2, 1. It goes 3 in the x direction, and it goes 5 up and down. Our goal for this question is to find this parametrization of the line, which basically means find a set of parametric equations that will model the line that goes from A to B. Okay, so I'm looking for my final answer to have an x equals, a y equals, and then some sort of interval. And that's how I know I'm going to be done whenever I have that. And we're going to use vectors to help us show how this actually works. Rather than what we did maybe in the warm-up, which would work and actually give us the right answer for this stuff, we're going to define it with vectors, and then we'll kind of work backwards and see if we could figure out what a nice shortcut is. So first thing I'm going to do is just define a couple things. And the first one is I want to know what vector A is. Okay, so vector OA is just going to be negative 2, 3, because that's what point A is. So hopefully you're okay with that. Next thing that I want to try to define is going to be this vector right here, which is the vector AB. I'm just going to put it up here because that lines up with how I wrote it in my notes. And just like with the warm-up, I'm going to do head minus tail, so I'm going to get 5, 3 when I do that one. It's important that this is what we're trying to find, is this dotted line that's right here that goes through A and B. And in order to help us achieve that, I'm going to put some arbitrary point that's anywhere on this line. I'm going to call that point P, and I'm going to give it an x, y point. Okay, so I'm saying I don't know what its x, y point is. I'm just leaving it as this point P with a value of x, y. And what I'm going to do next is connect this up here and write a vector for this one. So from the origin to point P, it's just going to be x, y. Now that we have these definitions, let's come up with one last one, which is to try to define what AP would be. Okay, so that's going from A up to P, what that vector would be. Okay, which is going to get messy if I try to draw it in there, but that green vector right there. And what I notice about this immediately is that the blue vector and the green vector are going in the same direction, and the only difference between them is their length, okay? And I know what the blue vector is. It's 5, 3. So this vector AP is just some sort of multiple of the vector AB. And whenever we have just a multiple, we can express that by introducing another letter to represent what that multiple would be. So I'm going to choose, the letter T and say that AP is just some multiple of AB. And that's because they go in the exact same direction. Okay? So I just picked an arbitrary number to say that, hey, there's some amount that makes AB different from AP. I don't quite know what that is yet. And what we can do here is distribute that through and say that AP is just going to be 5t comma 3t. Okay, so I now have this AP that's traveling in the same direction as AB, but it's some sort of multiple that makes it either bigger or smaller. It doesn't matter. T could be a smaller number than 1, and that would make it shrink in case this point P was like here, and it would be smaller than AB. Now we have all this basic stuff set up. What we're going to do is use the triangle that we just formed here between the red vector, green vector, and purple vector. So the red vector, which is the vector OA, I don't really have a lot of room here to write this, so I'm just going to write it down here, OA, plus the green vector, which is this vector right here, so AP. That's going to equal this purple vector, and that's just basic vector addition. And I actually don't need this drawing over here anymore, so I'm going to move it out of the way so that I can rewrite this stuff up top. So I have OA plus AP equals OP. And if I fill in with all of these things over here, that's 2, 3 plus AP, which is right here, 5t comma 3t equals OP, which is x, y. And we know by vector addition that we can just combine these, and that will equal the x value over here. So x would equal -2 plus 5t. Y would equal 3 plus 3t. And here we have a set of parametric equations. Because it's a line and lines go on forever, we can add the interval, which is the last thing that we need. So this will give us a set of parametric equations that moves us from point A to point B. And there's a couple things that I want us to connect to this so that we can see where these numbers are coming from in a much easier way than having to deal with vectors. Our goal is to not use vectors again. So let's see if we can figure out where this 5 comes from, and we're going to connect this back to the warm-up. So the change in the x values from the original point A, which was at -2, 3, to the point B, which was 3, 6, the change in the x values would be 3 minus a -2, aka 5. And let's look at the change in the y values. It would be 6 minus 3, which is 3, so that's right there. And where did we actually start? We started at the point -2, 3, and here is -2 and 3. Just ruined my green marker by getting a black marker all over it. So there's one last thing that we need to think about, which is what about the t value here? Because in the warm-up we had delta x over delta t. So if we're letting this value right here be 5, which is what that is, what we're assuming, okay, here is we're assuming that delta t equals 1, because we weren't told otherwise. They didn't say find the parametrization of the line through these points that takes 3 seconds. They just said find the parametrization. So we're just going to assume that it takes exactly 1 time unit to move from the starting point to the ending point. And that way, our rate of change is just what delta x is and delta y. If I were to write these in formulas for you, what we might have here is x equals the starting x position plus the change in x times time. And I typically write this the other way around. So I would write delta x over delta t times the variable t plus the initial x value. Same thing with y. It would be the change in y over the change in t times t plus the initial y value. Okay? And this is our best friend. This is the equations that we're going to use for 99% of the lines questions that we're dealing with. We have a slope times the variable plus a starting value, slope times variable plus starting value, and this should basically remind you of y equals mx plus b, where m is the slope and b is like the starting or the y-intercept. It's the same exact idea. We have the change in the x value, and then we have its starting position. It's just not necessarily an x or y-intercept this time. It's just wherever the point is. So that's the equation we're going to use moving forward. So for part 2, we want to find the parametrization of a line segment, which means that we have a start and an end point. So we're going to allow it to start at A and go to B, and that's because it says from A to B. So A needs to be our start, okay, and B needs to be our end. And let's just use the same equations that we already found. Okay, so we had x equals 5t minus 2, and we had y equaled 3t plus 3, I believe. So let's just figure out right now, before we look for a nice connection here, like what t value makes this happen. And we can do that by just setting this equation right here equal to the x value that we want to find out. So the x value here is -2. So at what time will this equal -2? And that's going to be when t equals 0. Because if t equals 0, then x equals -2. And the same exact thing happens for y. I really don't need to check y because remember, these equations are linked. So once I found the t value that works for x, it automatically works for y. But let's just show you. If we start at y equals 3, when t equals 0, then we will have y equals 3. So we know that this thing needs to start at t equals 0. Let's figure out, by the same exact kind of logic here, when does it end? So I'll use the x equation. X has to equal 3 because that's the ending equation. And I want to know at what t value does that happen. So I'm going to add this over. I'll get 5 equals 5t, so t equals 1. And we could do the same exact thing. Let's just test it by plugging in t equals 1. I'll get 3 times 1 plus 3, which is 6. So this worked. So I know that this is going to end at t equals 1. And that should make sense to you, actually, because what did we assume delta t was? We assumed delta t was 1 because they didn't tell us otherwise. And the way that this equation models itself is that when t equals 0, we'll be at the start values, and then whatever delta t is, that's going to move us to the end point. So in order to be done with this question, all we do is we have our same exact equations, but this time instead of going from -infinity to infinity, we're going to go from 0 to 1. And it's or equal to because we want to, start and end at those values. So for part 3, they change things up. They now say that we want to make sure that A starts at 0 and that B does not end at 1, but that B ends at t equals 4. So that's going to change our delta t, which is now going to be 4 minus 0, or just 4. And over here, it's going to change our equations as well, but very subtly, because all we have to do now is just add the delta t as no longer being 1, but being 4. So I can just divide that by 4, and divide this by 4, and then change the interval to make it go from 0 to 4 now. And that's actually it. It's done. So I'm just going to write it cleanly, just because it's a little bit messy up there, but I'll have 5/4 t minus 2, and then I have y equals 3/4 t plus 3, and this will go from 0 to 4. And if you want to check it, just plug in 0, you'll get -2 and 3. If we plug in 4, the 4 is going to cancel with the 1 on the bottom, so we'll have 5 minus 2, which gives us 3. Same thing here, 4 and 4 cancel, 3 plus 3 gives us 6. So this delta t value, all it's doing is slowing down the rate of change. Instead of allowing it to move 5 units in 1 second in the x direction, it now makes that same amount of time take 4 seconds instead of 1 second. So we're slowing down the rate of change, staying at the same exact start point, and it just slows everything down for us. All right, for our application question here, we have Bea jumping out of a moving car, as Beas do, at the coordinates of 41, 10, and she begins to run 2 feet west, 1 foot north per second, and continues on this linear path at a constant speed. Okay, so it's linear, So we can use our formulas. So I'm going to write her equations by just doing x equals, her rate of change was 2 feet west, which is in the negative x direction. So that's going to be negative 2 times t plus the starting value. She started at point 41 in the x value, y value. Going 1 foot north, that's a positive 1 times t plus her starting y position. And that is Bayes' equations. Next, let's see, we have, Marissa hiding in the bushes. That makes sense, definitely. So Marissa hiding in some bushes at the x and y values of 6 and 3. So let's just start off by writing those 6 and 3, both positive. And when she sees Bea, she starts moving 3 feet east, okay, which is in positive direction. So that's going to be 3 times t, and 2 feet north, so 2 positive. And let's see, the only other thing we need to do is that we're just going to assume that t is greater than or equal to 0, so we don't have negative time here. So here are our set of parametric equations to model Bea and Marissa in this particular situation. So what we want to try to figure out next is, are they going to collide? So we could figure out normally, okay, so like with normal rectangular xy coordinates, whether their paths cross. We would have like one person going this way, we would have one person's going this way, and we would say, okay, the lines intersect, but what we want to know is, do they actually meet? Because remember, we now have time going on here. So if one person is moving, we have to take into account each one at maybe an interval of 1 to see whether or not they actually will cross at the same moment in time. So we need to know, where is that intersection happening? And there's a couple different ways of doing this. The easiest way for us is to basically figure out when the x values equal. Okay, so that's what I'm going to do first. I'm going to set Bea's x value equal to Marissa's x value, and I'm going to see at what time their x values are equal, just their x values. Okay, so I'm going to do negative 2t plus 41 for Bea and 3t plus 6 for Marissa, and do a little bit of solving here. So that's going to be 35 equals 5t. So t is going to equal 7 seconds here. So their x values are equal at 7 seconds. But what we don't know is, at 7 seconds, is the y value equal for both of them? Okay, because we know that maybe their x values are equal at t equals 7. So let's just make an arbitrary t equals 7. So maybe their x values are equal right here. But if their y values aren't equal, then they're not going to hit each other. So all we do is just plug in t equals 7 into both equations and see whether or not they're equal or not. So let's do y of Bea, plugging it in at 7. So if we do that, that's going to be 17. And if we do y for Marissa at 7, that's going to be 2 times 7, which is 14, plus 3, which is 17. So yes, they are going to collide with each other, because when their x's are equal at time 7, their y values are also equal. And that's basically the process we do for colliding. Every time we just set the x values equal to each other and find the time that happens, and then compare the two y equations.